My name is Jamika Marshall, and I am the Shadow the Scientist Coordinator. It is my pleasure to welcome you to our very first session hosted by J.D. Armstrong of the University of Hawai'i Institute for Astronomy, as he will be allowing us to shadow him as he tracks newly discovered asteroids using the Las Cumbres Observatory robotic telescopes. JD, thank you for being with us today, and you are now the session host. Take it away.
Wonderful. Well, thank you for inviting me. It's wonderful to be here. And for just a comment to those who have signed in, we are encouraging questions. Feel free to ask. If they get, if we get too many, we'll manage them, but I doubt that'll happen. It'd be good to hear from you. So let's see here. I'll share my screen here. I've got a cartoon up here that I kind of liked. This was put up in response to the DART mission, cartoon that was in response to the DART mission, and I did some observations related to that, so thought I would put that up instead of my boring screen. Okay, so what we're going to be doing today is we're going to try and program some observations on Las Cumbres Observatories. And what we will be trying to do is to recover near-Earth asteroids. So I hope that you've had a chance to look at some of the things that, some of the background videos we posted. But basically, the idea is that the Earth has been hit by big rocks before, and we kind of don't want to be wiped out by a big rock hitting the Earth. So we're going to look for them first and hopefully catch them before they hit us, so that hopefully we can divert them. And so I'm going to start off by going to the Minor Planet Center here. You can just Google Minor Planet Center if you want to find this. And they are in charge of keeping track of all the things that orbit the sun, basically, and they have this NEO confirmation page. So we've got all these, each one of these is a newly discovered asteroid, and the first column is the name of the asteroid. That's just, given an identification number, they'll if they get around to it, they'll give it a more creative name. These are just numbers. I can recognize this is from Pan-STARRS, which is here on Maui, which is kind of cool. This also is Pan-STARRS. You'll notice the letter P is what's tipping me off. Don't know these guys. This is Atlas. This is another telescope. One of their telescopes is here on Maui. Another one is on the Big Island, and I think they've got one in Africa and maybe Chile. I can't remember. So these are the two University of Hawaii studies, but we're going to select all of them. And we're going to specify a telescope. I happen to know all the codes because I've done this so many times. We're going to try to do W as in whiskey 85. That is a telescope on Las Cumbres network that is down here. Okay. And so we're going to do whiskey 85. Okay. Now what this gives us is, here's the year, month, day, and hour. And then here's the right ascension and declination. This is like longitude and latitude in the sky. Just think of it like that. This, where it says V, is magnitude. It's how bright it is. And V is for visual. It kind of is, there's a filter that's called a V filter. It's actually kind of green. And so a V of 19, we can see as faint as a magnitude of 6. Now that probably doesn't make a lot of sense. So let me explain magnitudes. There was a guy named Hipparchus, and he must have been bored one night. I'm going to guess that the internet was down. And Hipparchus was one of these guys that ran with Socrates and that crowd. So when the internet was down one night, probably was bored and looked up at the stars, and he said, okay, well, that's the brightest star in the sky. And well, these are the second brightest stars in the sky and third brightest stars. And of course, somebody had done that before. A lot of people had done that before, but he did something very clever. He wrote it down. And then he did something even more clever, which was share it with his friends. So in other words, he published. So the fact that he published it basically means that he gets credit for doing this. But then we kind of used this system where the brightest star is 1 and the faintest star you can see without a telescope is 6. And so brighter things are smaller numbers, more negative numbers. So it's kind of weird. And each one of these is a factor of 2.5. So magnitude 1 star is about 2.5 times as bright as a magnitude 2 star. And a magnitude 2 star is about 2.5 times as bright as magnitude 3. So this is quite a bit fainter than the human eye can see. Okay, but that's the whole point of telescopes. They can see things this faint. But what I need to do is I need to calculate, asteroids are moving. So let me see, do I have a quick, oh, I can let you see the Wiggins thing. Or no, I'll lie to you guys. You guys will pretend that you think that this is an asteroid. This is actually a satellite. I don't want to show you that GIF because it's not as nifty. It's not being cropped up. Okay, so, all right, you all right seeing that animation there? That is actually a satellite, but this is about what an asteroid is going to look like in the telescopes. Now the asteroid is moving, okay? And we need to figure out, well, how long can we take a picture before it starts getting some real motion streak? So in other words, before it starts looking like a line. Let me see if I've got, should have thought of this before. Got another nifty, here it is. All right. So without reading the name of that, does anyone know what this is? Probably not. That's actually the SpaceX Tesla. And what's going on is we took the images too long, and so our dot got stretched out. We got motion blur. And if you get motion blur, it's harder to measure the position, and it doesn't help us see at all. So there's no point in exposing for too long because it doesn't help you any, and it does make life more difficult. So I know that we can only move about 1.5 arc seconds. And so this is the speed. This is how fast it's moving, how fast the asteroid appears to move in the sky. This is an arc second, and that's like an arc second is a very small angle. And this is a minute, and minute is unit of time. And so this is kind of like a speed in the sky. We can only move about 1.5 arc seconds before we start getting that blurring that we were seeing on that streaking that we were seeing on the Tesla. And if anyone's wondering, the reason that the Tesla is streaked is, well, I screwed up the calculations when we were doing those observations. but it still turned out to be a great project. The kids that I was working with got first place at the Maui County Science and Engineering Fair. I was really proud of them. Okay, so we can only go about 1.5 arc seconds. So we're going to do some calculations here. If it'll let me open up Paint. Again, noting for the next time I do this, have these open. It'll look more professional, but you guys are pretending that I'm professional, right? Okay, so we have 3.95 arc seconds per minute. And that's like the speed or the velocity. And the distance is 1.5 arc seconds. So distance equals rate times time, or actually that we should say velocity in here, because that's what we're using here. And suddenly someone in a physics class out there is probably going, wait, this is really useful. Yeah, it really is. Okay, so how long can we observe for before we get noticeable streaking? And so that the time is equal to the distance divided by velocity. And I'm going to round this to about 4 arc seconds per minute. Okay, so distance divided by velocity. We've got the distance is 1 point, and that's equal to 1 point, a decimal. Okay, I can draw a decimal place. 1.5 arc seconds divided by 4 arc seconds per minute. And notice I'm going to treat these units like variables. Units are very important because a friend of mine, Dan Magestro, no, it was Ted Foringer. Ted was a friend of mine when we were in grad school, and we were taking the qualification exam, which is you have to pass this exam or you don't get your PhD. You stop in the program. And they came up with a question that he did not know the answer to. And so he looked at it. They asked him about drag, about viscosity and drag, like air drag, air resistance. And they probably asked him that because they knew he was a pilot, had a pilot's license, and they probably figured that he'd know it. And he didn't, but he knew the units. And so from using the units, he was able to put together the equation he needed and answer the question. And he claimed that the only reason he passed the qual was because he was so good with units. And so Dr. Foringer is Dr. Foringer because he was very careful with his units. So very important to have units. Now, so I've done the math. I used Google Calculator to get this number. I can't do that in my head that quick. But this is equal to, let's see here. So I want to change this to seconds. To change it to seconds, I'm going to multiply by 1 creatively. So 1 minute is equal to 60 seconds, right? Okay, so I'm going to divide both sides of the equation by 1 minute, and I get 60 seconds per minute. And that's equal to 1. We can multiply by 1 and it doesn't change anything. So this is called multiplying by 1 creatively. So I'm going to multiply by 60 seconds per minute. Yeah, sorry, my handwriting's really bad on that one. The minutes cancel, and I get, putting this into back into the calculator, 22.5 seconds. Okay, 22.5 seconds. Well, I already know that this is not bright enough. If we only take a picture for 22.5 seconds, it's not going to be, we're not going to see that asteroid. It's just going to be too faint, especially right now. We've got a full moon and yeah. Okay, so I could keep going through this. I think that would just be painfully boring for both of us. So I'm just going to look. Okay, this is, so we've got about 2 minutes for that. I need, on a good night, a night without a moon, for a 21st magnitude asteroid, I need about 180 seconds usually. So that's not going to work. This isn't going to work. Let's see, we can go about 180 seconds on this. So for a good night, we might try that. I'm actually not going to try it for tonight or for today because I don't know. But basically, I'm not going to try it right now because of the full moon. And I need to start out my notes here. So I'm just navigating to that in my computer here. Okay. So these are all the asteroid kind of things that we do. Recovery. And I want a new folder. Taking good notes and being organized, so helpful as an astronomer. 2023 0930, because we use universal time. And in England, it is now the 30th. Well, it's just about the 30th. It's not, it's like 11:18 p.m. on the 29th. And I'm going to do a new text document. We seeing any questions?
Yes, in fact, we do have a few questions. JD, would you like me to read those
Yeah,
to?
that would be great. Yeah. Yeah, feel free to jump in with questions anytime.
Okay, I will make sure to do that, JD. Thank you. All right, so
Okay,
we
great.
have our first question is from Vani. Vani asks, how are asteroids named, JD?
How are asteroids named? Okay, well, the first thing they do is they give them a provisional name. Okay. Um, and this is an example from Pan-STARRS. And what Pan-STARRS does is, well, okay, if we're starting here, okay, this is the asteroid they just discovered. The next asteroid they discovered would be this, then this. They just kind of go through a numbering sequence. That's a provisional name. After the asteroid has been tracked, I think it's, check me because I could be wrong, but I think it's something like 7 opposition. In other words, 7 times passing it as we go around the sun. Then the person that discovers it gets to name it, but they can't name it after themselves, and they can't name it in such a way that it kind of looks like it's after themselves. For example, I couldn't name it after my father or mother because they share my same last name. I can't put Armstrong in there. Does that kind of answer the question?
Yes, I believe so. Vonnie,
Yeah.
if you need any follow-up to that explanation, just drop me a note in the chat. Okay, and the other question I received, I got a direct, so you all in the chat can direct message me with your questions also. That's great, thank you. Or you
Yes.
can put them in the chat and I will share them with GD. So the other question was just some background on Las Cumbres. Is there just one telescope you're using, or how do you choose which telescope you're going to use as you're tracking your asteroids?
Okay. Yeah. So Las Cumbres, there are telescopes in all of these places. So this is LCO Global. If you just look for to find this in a Google search, I do Las Cumbres Observatory Global Telescope, LCOGT. That used to be the name of Las Cumbres Observatory, but they changed it for marketing reasons that I didn't like. And they got their new logo, which I don't like as much as their old one. But anyway, um, so they have telescopes all around the world. They have 3 telescopes here on Maui, the 2-meter Fox Telescope North, and 2 smaller telescopes that are not terribly good for tracking asteroids, but really good for some other things. I've actually been doing some observations of asteroids with them, but to measure the brightness fluctuations, look at the rotations. This is the one that we were asking for. There are actually 3 1-meter telescopes here, W85, W86, and W87. Convenient. They actually worked with the Minor Planet Center to get those numbers for the telescopes. And the Minor Planet Center gives it those numbers. Let's see here. There's, let's see, 2 of the smaller telescopes here, 2 1-meters in Tenerife. This is actually a really good site. This is an even better site. This is an incredible site. It's questioned whether Haleakala or Cerro Tololo is better. Most people would say Cerro Tololo, but one of the engineers that works on Las Cumbres has told me he thinks Haleakala is better for the network. South Africa, this is a pretty good site. I do a lot of work with, do a lot of asteroid recovery using these telescopes. This is still being built, Tibet in China. And they'll have some 1-meter telescopes there. And then Siding Springs, Texas. The telescope here really is, I don't think is really on the network. It's called, it has the abbreviation BPL. So over here, Haleakala Observatory, this is OGG, that's our airport code. But over here, it's BPL, stands for back parking lot. And so they literally named it because it was in the back parking lot. It was used for testing. I love that. Okay, and the way we choose telescopes is we tell them what size and what filter or what instrument we want, and then they just and what time span to observe from, and then they choose a telescope for us. We don't get to choose the site unless there's some driving science reason. Then you can go in if you know how to and request a specific telescope or a specific site, but generally they don't want you doing that. They want this to be thought of as one single observatory, that it's not just a collection of telescopes, it's one observatory. All these telescopes are acting in concert. And it, for the most part, that's what it's like. There are a couple more things that I'm going to keep pushing them to do, like being able to carry over from one site to the next with a single observation. But for the most part, they really do kind of act like one telescope. Now, here, this one, so did that answer the question? We'll see. We'll program the telescope in a minute, and we'll see how that works. Okay, so I'm just going down the list again while I'm talking, and this is an interesting case. This one, moving so slow, we could definitely get to that brightness, but moving so slow, it would take a lot of telescope time to really get it. So I'm going to write this one down. I might put this on a different telescope. One that we tend not to have as much demand for. This is too faint for us to observe. Just barely moving too fast for this brightness. Let's see, too faint, too fast. No. And part of it is I'm going to be a little bit pickier. I don't know if this is every now and then the Minor Planet Center gets, one of these smaller surveys on it. And they, these smaller surveys sometimes don't do a great job filtering for false detections. So I kind of worry a little bit. Oh, we should look at the map too. So this is, I don't know the survey that's doing this. I've seen a lot of observations from these guys lately. I've tried a follow-up or two of theirs, but haven't had much luck. So I'm a little hesitant. They may be an excellent group. It could be just bad luck that I didn't see what they were looking for. Actually, this one, okay. So our field of view is about 1,000 arc seconds. So 1/4 of this screen here. Okay, and then this is based on the uncertainty of the measurements. They've calculated a whole bunch of orbits, and they're saying for each one of these orbits, they put a dot. So each one of these dots is where one possibility where they think the asteroid might be in the sky. And that's 400,000, 800,000. It's just such a huge spread that, we can only we can only see about that much of the sky. So I'm not going to bother with that one. Because there's just not much hope recovering it.
JD?
Yes?
If I could break in here for just a moment, I'd like
Yeah?
to take a few seconds to acknowledge my CREST colleagues that are in the audience. We have the Shadow the Scientist founder, Raja Guhatakartha here, who also has his hand up for a question, so I'll come back to him in just a moment. But we are also joined by Anand and Lindsay Lauber, who is also one of my amazing CREST colleagues. Shadow the Scientist is a CREST initiative out of the University of California, Santa Cruz. And Lindsay is our associate director. Anand Lalaria runs an amazing program along with Sierra Schneider, the science internship program. And I am absolutely thankful for their presence here today and for their support in all that we do. I would like to turn it over to Roger real quick, and then any of our CREST colleagues, please feel free to come on and introduce yourself.
All right.
Thanks, JD. Thanks, Jimmy. JD, thank you for hosting an STS session. This is our first session on asteroids and first session that LCOGT is part of. I think I had a chat not long ago with Lisa Story-Lombardi.
Oh, yes, yeah.
LCOGT getting involved. So I'm really happy to see this all coming together. My question was about the slow-moving asteroid. You said it would be expensive to follow it up just because it would take a while for it to move out of, to change its position appreciably in the sky. Is that right?
Yes, that's correct. What we're going to do
Yeah, could you just do two exposures that are well separated in time instead?
Potentially we could, but if I put two observing requests each with one exposure, well, it actually would be kind of valuable to do that because it makes the measurements a little bit more precise. The uncertainties don't affect as much. I generally don't do that because it's asking for two separate observations, and the scheduler might pick up one of them, but not both of them. And so,
and if it only picks out one, then it's wasted, right?
Yeah, it kind of is. If it's a target that I'm personally following up and personally tracking, I might do that because then I could go on to like Google Sky, and I could look and see if there was look around and say, okay, are there stars in all these positions? And if there's a dot there that doesn't belong there, oh, that's probably the asteroid. And sometimes that can be helpful. But for the minor planet center, that's just too human time intensive. It's just not reasonable for them to do that.
Got it.
But yeah, so I'm actually going to try this. Let's do this from Siding Springs on the 2 meter. So this is Echo 10. But yeah, thanks for reminding me of that. I didn't want to forget that asteroid. So I'm going to put in my notes that we're going to look at this in Echo 10. I'm going to replace these ephemerides. The asteroids are actually close enough to the Earth that looking at them from different positions, the asteroids will appear to be different places in the sky. So, okay, so I'm sorry, I'm interrupting the everyone doing their shout out here.
Wow. So even sorry, Jay, just to jump in on that, they're saying that even the diameter or radius of the Earth is enough of a baseline that you can see significant parallax.
Yes.
Oh, that's very cool.
Yeah, I actually had some middle school students that what we were doing was measuring the distance to a satellite, it was kind of comparable distances out to the satellite as to some of the nearer asteroids. And I've had students measure the distance to asteroids using this parallax, this different position we see in the sky. Okay. All right. So what I'm doing is I've gone into the Las Cumbres observation portal, and you have to have an account to do that. I happen to have one, so that's what I'm going to do. And you choose a proposal, IPP factor. I'm going to name the observation request with the name of the target, and then I'll keep going. Telescope size is a 1 meter. Did we have other shout outs we wanted to do?
I can introduce myself.
Okay,
Hi,
great.
my name is
Hi.
Anand Laria. I'm part of the CREST team. It's amazing to be here. I'm happy to be joining a STS session, and I've learned so much about asteroids. Thank you.
Right.
But I work with an amazing team, Sierra and Raja and the greater CREST team, and we run the science internship program. We just wrapped up our 15th year. It was a great summer, and now we're in the stage where we're preparing for SIP 2024. But back to the STS session.
Okay. Any other shout outs? Any other introductions here?
I'll say hello real quick. My name is Sierra Schneider. I'm the assistant director for the science internship program and have worked with Raja for a really long time in other projects. Even before SIP and with CREST, and just have been around all the conversations about Shadow the Scientist from the early days before it was even named that. So this is just really exciting to be here and see it in full swing and full force, and Jamaica, just everything, just it's wonderful. So thank you all so much for inviting us today and letting us know this was happening.
Yeah, well, thank you for coming. And thank you all for putting this together. I think this is a great program, and Jamaica really has been fantastic putting this all together. So, okay, let me go over what I'm doing on these observations real quick. So this is the name of the observation request. I use the target name. And then the next thing that is kind of important is the instrument. So I choose a size of telescope, and I'm going to choose a 1 meter telescope. We're going to come back to this dither because we would want, because when actually programming this in, I would need to enter the coordinates first and then come back to the dither. Based on this, I'm going to, I figure I can do about 180 seconds before getting streaked too bad. Okay, so I'm going to do an exposure time of 180 seconds. I choose a filter. The W band is the clearest filter. It lets the most light through. It lets all colors of light come through. And then I give it a target name. So the target name is, well, here's the provisional name of the asteroid. If I were doing something else, let's say I was doing the Orion Nebula. Watch how cool this is. If I were doing the Orion Nebula, it would recognize the nebula and it would automatically put in the right ascension and declination for me. I think that's just really cool. But we're not doing the Orion Nebula, and it doesn't recognize these asteroids because, well, they're too new to be in the database. So I have to put in the right ascension declination, which is really no trouble, but it's just kind of cool when it recognizes things like that. Technically, we could go in and we could track non-sidereally. We could actually have the telescope follow the asteroid. And if it was really important to get an asteroid that was faint, that's what we would do. That way the stars would be streaked instead of the asteroid, and it would be reasonable to make the measurements. The other thing is we could track at like half the rate of the asteroid, and then the stars would get as much streaking as the asteroid. And so you can kind of split it up and get about twice as much time. All right, this is, and then down here, this is the window. This is the window of opportunity where we are saying, well, don't start the observations before this time. And if you can't finish the observations by this time, then just give up. Don't worry about it. Okay. And we were asked, we had a question about, how do we choose which telescope? Well, we just kind of have a little bit of an option here because like McDonald Observatory, let's say I don't want to observe on McDonald Observatory. Well, okay, I can just set this time back a little bit until suddenly, oh, it has the McDonald Observatory can't observe it. So what we're showing here, up and down is like how high it is in the sky. Left and right is the time in universal time. Where you have a solid line, that means that you can observe from this observatory at that time. And this green one is Sutherland. I like the Sutherland Observatory. The blue is Telluride. That's the Tenerife. That is also one that I like. I've done quite a few asteroid recoveries from both of these.
JD, is Sutherland in South Africa then?
Yes, Sutherland is in South Africa. That's correct.
Yeah. Near Cape Town?
Yeah, it's near the Salt Observatory.
Oh, near Salt. Okay.
Yeah, it's like Salt Observatory.
South Africa Large Telescope, right? Okay.
Yeah. At least that's my understanding.
Okay, and sorry for jumping in.
No, that's great. That's great. And so I like either one of those telescopes, so I'm kind of happy with this. Now I'm going to make sure that I've chosen some coordinates that are pretty close to the center of that time, because asteroids move, and well, yeah. So but at 7 o'clock. Okay, we don't want to go that late. We want to go more like 4 o'clock. Oh, that's right, because we chose South America, Chile. And I might want to go back in and double check this, but the parallax for asteroids shouldn't be killer for us. So we're just going to go ahead and leave that. And the next thing I'm going to do is, now we've just programmed it for one image. I could tell it, hey, just give me 4 images, but I'm going to dither it. I'm going to move it around a little bit. That way, if there's some sort of little schmutz on the, some little defect on the camera or a little fleck of dust somewhere that looks like it could be an asteroid, it's going to, by dithering, I'm going to have it move in a square pattern. I'll show you just a sec. Here we go. So it's going to start here. It's going to shift up just a little bit, shift to the left just a little bit, shift down just a little bit, just enough that it'll shake up any little blemish on the camera that looks like an asteroid. And I'll be able to look at it and say, oh, it's moving wrong. That can't be an asteroid. It's just a good way to double check your work.
This is just bad pixels on the detector where the doping of the silicon might have been non-uniform or something like that.
Yeah, something like that. Or if like there was a fleck of dust when the flat fields were created and that fleck of dust goes away, suddenly you can have kind of a bright spot in the processed image. Yeah, yeah. So, okay, so this is, it's going to take me 15 minutes, 44 seconds of time. That's worth it. If we get that target, I will be very happy. Let's just do one more. Let's do this on the 2-meter telescope in Australia. Couldn't remember which one we were doing here. So this is Siding Springs Observatory in Australia. There are only 2-meter telescopes on the network right now, the Muscat and the Spectral. We'll look at some Muscat observations in a minute. They're really awesome. And, oh, that's right. We're going to go for a fairly long exposure with this. I'm going to go with 5-minute exposure. This is the broadest filter they have that covers the largest spectral range and will give us the most sensitivity. Again, the name of the target. It doesn't recognize the target. Yeah, we know that. Copy the right ascension declination, and I'm going to put it up here. So I've got it in my notes as well. Note that it is very important. Notes, however you do it, you've got to do good notes in science. Okay, so there's that. And save this file. There we go. Okay. And see, there we go. There is Siding Springs, Australia. And we were looking at 12 o'clock. So right here. Oh, that should be fine. It's a very slow moving asteroid. And so we're going to go to dither. I'm going to put the dither again. I'm going to do a grid because I like grid. 2 arcsecond spacing, left to right, 2 arcsecond spacing up to down. I'm going to do, should we do 2 rows and 3 columns or 3 rows and 2 columns? Who wants to vote? It doesn't matter.
3 and 2.
3 and 2. Okay, there we go. Basically, that'll just give us, yeah, I want to do 6 images to cover the time. And so that's what it's going to look like. It's going to go up and over. And then I'm happy with that. This will take half an hour. So half an hour, it'll move. Yeah, that'll be enough time to actually see the motion. All right, so we just programmed a $30 million telescope to go look for a rock. And it's not even a shiny rock. And if we find it, we don't even get to keep it. Oh, it's terrible.
And JD, would this, would a good equivalent of this, what you're doing, be like, let's say there's a very slow moving plane in the sky. And if we wanted to take 2 images that are separated by a few minutes, we would see that plane move relative to, let's say, the stars. Is this equivalent to that, something like that?
Yeah, that's very much what we're doing. It's exactly right. We want to see the motion among the stars because that will tell us that this is indeed an asteroid.
Right. And the stars act as an anchor for a reference frame that is
Yes,
is insensitive to the rotation of the Earth, for example.
right. Yes, exactly right. Let me see here. Give me a moment. Let's actually take a look at some observations that I got last night. So I've already downloaded this one and this one. This one, was this the one on? Yeah, so this is on the Muscat camera. This is a really cool camera. It actually has 4 cameras on the same instrument, and it divides the light up by color. And when it does that, it and then it takes 4 pictures in each color band, in each color range, or 4 total pictures, 1 in each of the color ranges. And so you get 4 pictures for the price of 1 with this. It's really kind of nice. And so we'll start off with that one. Okay, so here's my folder. This is the observations we just did. And here's this one is the one we want. Oh, no, this is the one we want. Okay, we're gonna look. Okay, this is a program called Astrometrica. This is kind of on its way out a little bit, I hear, but I still really like this program. When it works so well. It's really cool. Does a lot of the work for you. You have to tell it a little bit about the telescope so it has a good initial guess as to where it's pointing. So I have a Muscat red camera configuration, and tell it, okay, yes, save changes. And then I've downloaded these images. I've converted them and done a little bit of processing on them since they were in Las Cumbres' hands, and go in here to fit. And so we are going to play Where's Waldo with an asteroid. Does that sound fun to everyone? Okay, I'm hoping there's a lot of cheering going on, but I can't hear, so. All right, so I just load these into Astrometrica, and then I click on what I call the green bullseye. This is astrometric data reduction. The program is looking at all the stars that it sees in the image, and then it compares it to a catalog of known stars, and it uses the position of those known stars to determine where every pixel on this image is. And we can actually measure the position of an asteroid to like better than half a pixel on on the images. It's really pretty impressive. So we want to know if it's an asteroid. We're going to have to see it move, because as far as I could tell, if this were just one image, I could be looking at this star and thinking, well, that could be an asteroid or it could be a star. But it's not moving as I blink the images. So we're playing these like a looped movie, and the star is not moving. So it's probably not an asteroid, or it's something really far out there, but that's not what we're looking for. So I'm going to start in the middle because that was the predicted position. And I actually see it. Okay. A lot of you are probably going, oh, there it is. Actually, let's stop on that. This little glitch, this little thing right here, that's actually a glitch. Okay. Reason I know that is it's really, really sharp. Okay. Compared to a star. Let's look at a star. Hello. Wow, that's cool. Let's try that again. There we go. Okay, so this shows the brightness up and down versus position left to right. Okay, and it looks a little bit like a Gaussian profile. And the width of this Gaussian will be the same no matter how bright the star is. It's just anything above, say, this line here is white. And as you observe longer, you get more light from a star, it looks like it gets bigger. But it's actually, in reality, it's much smaller than 1 pixel. So so full width half max is about 1.3 arc seconds for a star. And if we go back to that glitchy thing, here's that glitchy thing. I think that was the one we were looking at. Full width half max, 0.4 arc seconds. So that's not a real object. Another reason I know it's not a real object, it only appears in 2 images. So it's here, it vanishes for 2 images. So that's not it. But up here, if you'll notice, just below the satellite path, that's probably a satellite. So, hey, thanks, Elon. Thanks, Mr. Musk. Okay, I'm probably blaming him for someone else's satellite, but you know, we do that. But this is the real thing about satellites. They will get in your images like that. So that to me looks like a real asteroid. The full width half max is reasonable. This is about the magnitude of the target that we were looking at, what we were looking for. So you'll notice that I did the exact same thing when programming these in as I was just doing with you guys, you know, keeping notes. And this was, yeah, so this was this one. So I'm going to just copy this. Okay. And so 21.3 magnitude is what they think it should be. 20.7 to a lot of astronomers, they're going to say it's pretty far off in magnitude. But considering the methods we're using to measure the brightness, it's close enough. I'm going to paste that in here. Basically, this is the name I'm giving this object. Oh, actually, I have a bit of a database on here, and so I can look and see if this is a known asteroid. That actually is one of the first things I would typically do. Okay, so the closest thing is this, and it's like 16 arc minutes away. That's not our target. If that's our target, the orbit is really messed up. So this is probably the target we're looking for, because that would be an unknown asteroid on that catalog. And we're going to step forward and we're going to click on it again. It's the same object, so we give it the same name. And you'll notice that you kind of have to have sharp eyes a little bit for this. One of my friends, Dr. Marco Michele, comments that, you know, 1 out of, I think it's 10 or so people are really, really good at spotting asteroids. Everyone else, the rest of us have to learn to do it. And even then, we're not as good as that 10%. And he doesn't know why. Sometimes they're really, really smart people, and sometimes they're not so smart people. Sometimes they're really intense people. Sometimes they're really relaxed people. You know, he just doesn't know why. So I'm just going through and looking because there may be other asteroids in here. And if there are other asteroids that are in here, it's possible that they are something that the Minor Planet Center needs observations of. And if that's the case, we want to send them the observations because, well, it's not free, but it's pretty close. And okay, so I don't see any others. Now, I always want to check that my the registration worked out correctly. So I come down here to a star and I call this creatively star 1. And I click on accept. And then I'm going to look at the Minor Planet Center report file. This is all the measurements we're doing. I'm going to grab the right ascension and declination here. And then on Google Earth, I'm going to flip it up to Google Sky. And am I right that we've got about 5 minutes remaining?
Yes, that is correct, JD. And
Okay.
we do have a few questions. I'm going to leave that till maybe the last minute of your session, if that's all right.
Okay. Yeah, whatever you want. Whatever makes people happy. That's what I'm here for. Okay, so that star, yes, that does match up, I think. That star, and then there's a little guy off to the side here. And so I don't know if you knew Google Earth did this, but yeah, it does flip around to Google Sky. Okay, so that's a match there. I'm going to match the other corner just to be extra careful. I like that star. And we're going to creatively name this one Star 2. How boring. One of these days I'll think of a better name to give it, but it works. View MPC report file. And right here, copy this. No, not into there, into here. Jumps up here. Okay. That looks like a match. So just verifying that we actually did get the registration correct. The next thing I would do is I would jump over to the Minor Planet Checker. This has the most up-to-date list of asteroids that are known to the Minor Planet Center. Don't minimize that. I'm glad I didn't close that. File, view MPC report. Just going to grab one line from here. And I'm going to say, hey, guys, do you know what this is? And probably they're going to come back and say no. So at this point, I would kind of take this and I would put this in an email to the Minor Planet Center. So, okay. I would change the acknowledgement here. I want to say, hey, yes, I did use the Near Earth Object Confirmation page. Got to give the Minor Planet Center credit where credit's due. And this is the target I'm looking for. Then I usually use this as the subject of my email. And then I would literally just copy this and paste this into an email and send it to the Minor Planet Center. Okay. No known minor planets brighter than Victor 24. So it's magnitude 24, found within 5 arc minutes. So yeah, this is an unknown asteroid. Most likely is the one we're chasing. So that's kind of cool. We actually found it. And let's see if they're still looking, if people are still saying, hey, we need to find this. Yes, it's right here. Low score, which means it might not be a near Earth object, but that's okay. We need to rule those out as well as confirming others. Okay, let's go to the questions.
Okay, this has been fantastic. All right, Rob, thank you so much for being with us. Rob is one of our very usual customers here in our shadow sessions. It's always
Hey,
so
Rob.
good to have you. And so Rob says, since Earth satellites move much faster on the sky, they should only affect one of the series of asteroid images, correct?
Yeah, that's what we're seeing here is, let's go back and take a look here. So where was that? Yeah, there we go. So, right. Yeah, it depends on most satellites. Yeah, if they're orbiting the Earth, they'll move pretty quick. And so in the time that we exposed this image, it went across the entire image. And so it was out of the field of view by the second image. So that's exactly right.
Thank you so much, Dee.
Mhm.
And one more follow-up. Can a regular person get an account to use Las Cumbres Observatory? How does that work?
So the Las Cumbres Observatories, they give time, you can submit a proposal to get time on it. Educators can get time on the 40 centimeter network, which actually, like I said, it's actually pretty cool. You can do some neat things with it. And another, an individual might be able to get some time on the 40 centimeter network, like a student or someone like that. There's another project that is related to Las Cumbres called Photon Ranch. I'm going to plug this because I know Wayne, who founded this, and this is going to be more of an educational network where you're basically where students would sign in. They would have to do assignments to earn telescope time, but you use some of your telescope time to do the assignments, and then you get to do the fun projects that you wanted to do as well. And probably knowing these guys, if you came back and said, well, can I do a project on this? They might go, okay, here, skip to this unit. That's close enough. But they want it to be this one, they really want to be educational. They don't want the scientists using all the time on this network. This is more for the scientists. So whichever one fits your needs. If you're a scientist, go for this one. If you're a student, go for the and or educator, go for the other one.
Fantastic. I really enjoyed this first tour of the capabilities of Las Cumbres Observatory. For me, of course, I've worked with you as we were planning this session, and it has been so much fun to work with you, choosing objects, seeing how to acquire the targets, and all the different details that go into making the decisions around which telescope to use, and then the excitement of getting that data back to confirm what you were looking for. Yeah. Thank you for allowing us to shadow you today, JD, and we look forward to shadowing you again in future sessions.
All right. Thank you for joining us. Hui ho. I will hope to see you all soon.
Thank you all, and aloha.